At the subatomic level, chemical bonds are the attractive electrostatic forces that bind isolated atoms and ions into more complex structures. This interaction is governed by a baseline axiom: the universe tends toward a state of minimum potential energy, or thermodynamic stability. In their isolated forms, elements exist in a high-energy, unstable state. By forming bonds, they release energy and achieve a more predictable, lower-energy configuration. We can track this stabilization by looking at the outermost edges of the atoms, where elements negotiate the arrangement of their valence electrons. Bonding is the physical mechanism by which these restless elements resolve their energetic instability. The Lewis concept identifies the benchmark for this stability as the electron configuration of a noble gas. The octet rule defines stability as possessing 8 valence electrons, a point of minimum potential energy and stable equilibrium. We see this drive by comparing stable neon with its complete shell to highly reactive sodium, holding 1 outer electron, and chlorine, holding 7. Because their valence shells are incomplete, these atoms are at a higher energy state, driving them to interact with others to fill their octets. This universal requirement for a stable electron count dictates the specific methods, transferring or sharing, that atoms use to construct stable matter. The ionic bond achieves a stable octet through a complete transfer of electrons from one atom to another. This occurs when a metal with low ionization energy encounters a nonmetal with high electron affinity. One atom is energetically eager to give up an electron, while the other is hungry to capture it. As they interact, the valence electron of the sodium atom detaches and locks into the vacant slot in the chlorine atom's valence shell. This transfer of charge creates a positive sodium cation and a negative chlorine anion, generating a powerful electrostatic attraction. In a bulk sample, this attraction extends in all directions. Millions of alternating ions snap into a repeating 3D crystalline lattice. This is why ionic compounds, like table salt, form expansive networks rather than small, independent molecules. The strength of these electrostatic attractions results in high melting points. Though the rigid alignment makes the materials brittle, a slight shift in the lattice can align like charges, causing the crystal to fracture. When two nonmetals interact, neither has enough pull to completely remove an electron from the other. Instead of a transfer, they achieve stability through a covalent bond, a mechanism of mutual sharing. Take 2 chlorine atoms. Each has 7 valence electrons, and each needs 1 more to reach the stable octet configuration. As the atoms approach, their electron clouds overlap. 2 unpaired electrons move into the central space, pairing up. Because the pair is shared, both atoms count those 2 electrons toward their own octet, satisfying the requirement for stability. This mutual sharing results in the formation of distinct, independent molecules, rather than the continuous grid seen in ionic compounds. Covalent architecture allows elements to stabilize each other by sharing the energy cost of maintaining an octet. It is a common mistake to assume that all covalent sharing is equal. The distribution of shared electrons is actually controlled by electronegativity, the specific strength with which an atom pulls on a shared pair.
In an H2 molecule, the 2 identical atoms pull with equal force, resulting in a symmetrical, non-polar bond. But in hydrogen chloride, the significantly more electronegative chlorine atom pulls the shared electrons toward itself, distorting the electron cloud. This creates a polar bond. The chlorine end becomes partially negative, while the hydrogen end is left with a partial positive charge. Bonding is a spectrum. The greater the difference in electronegativity, the more the bond shifts from equal sharing toward a complete ionic transfer. These partial charges alter how a molecule interacts with its environment, influencing its boiling point and its ability to dissolve other substances. A special case of sharing occurs when the 2 electrons in a bond do not come from both atoms, but from just one. This is the dative bond. In this scenario, one atom provides a full lone pair of electrons to be shared with an atom that has an empty orbital. We can see this in water. Oxygen has 2 non-bonding lone pairs. When an electron-deficient hydrogen proton approaches, it has no electrons. Oxygen donates its lone pair to the proton, shown with an arrow, forming the hydronium ion. Unilateral donation allows atoms and ions with significant electron deficits to reach a stable state by utilizing the existing pairs of a donor atom. Dative bonds are essential for completing the octets of molecules that would otherwise be unstable. Consider carbon monoxide. Carbon has 4 valence electrons and oxygen has 6, totaling 10. Even after forming a double bond, carbon only has access to 6 electrons. The octet is only achieved when oxygen donates a full lone pair to the bond, creating a triple bond. Similarly, in ozone, a central oxygen atom uses one of its lone pairs to stabilize a third oxygen atom that lacks a full octet. In this interaction, ammonia has a lone pair, while boron in BF3 only has 6 electrons. The nitrogen's lone pair bridges the gap, allowing boron to reach 8 electrons without contributing any of its own. This mechanism allows for the creation of stable structures in scenarios where standard equal sharing is mathematically impossible. These microscopic bonding behaviors dictate the large-scale physical properties of every material on Earth. This matrix highlights the differences. Ionic bonds result in high melting point solids due to their extensive lattices, while covalent compounds are more likely to be liquids or gases because their molecules are independent. Conductivity also changes based on bond type. The fixed ions in a solid crystal cannot carry current, but once melted or dissolved, those ions move freely. Covalent molecules, which don't have charged particles, do not conduct. We can map these properties directly to our common examples: sodium chloride, water, and coordinate complexes like the ammonia-boron bond. The specific method of electron stabilization determines whether a compound will be a rigid crystal, a fluid liquid, or a non-conductive insulator. Whether through the transfer of ions, the mutual sharing of a covalent bond, or the unilateral donation of a dative bond, all molecular structures are the result of the drive for thermodynamic stability. By seeking states of minimum energy, restless individual atoms assemble into the stable, functional compounds that define our physical environment. These 3 bonding forces provide the physical logic that allows a limited set of elements to assemble into the varied chemical landscape of our universe.